Now that we've derived the Lorentz transformation, let's take a look at some of its consequences, which are time dilation and length contraction. At the end of this video, we'll talk about how time dilation and length contraction affect muons, which are subatomic particles that travel close to the speed of light. If we accept that the speed of light is invariant in all inertial reference frames, then we have to accept the Lorentz transformations. And if we accept the Lorentz transformations, then we have to accept the idea that different observers will measure time and space differently. This brings us to time dilation and length contraction. Roughly speaking, time dilation is the effect that moving clocks run slow, and length contraction is the effect that moving rods appear short. To explain this video will make use of the space-time separation vectors that I introduced in Relativity 103b on Galilean relativity. Recall that the space-time separation vector is just an arrow joining two events in space-time, such as Albert Einstein sneezing and Richard Feynman snapping his fingers. When we measure the components of this vector using our space-time basis, we get the components 3 and 4. It tells us that Richard Feynman's snap happens 3 seconds into the future and 4 meters to the right of Einstein's sneeze. In this video, we'll see that time dilation is just measuring the same spacetime vector in two different reference frames. In different reference frames, the vector has a different time component, and so different reference frames will measure the time between two events differently. This first reference frame is moving with the clock, and it counts 3 clock ticks, or 3 seconds, along the vector s. The second reference frame is moving with respect to the same clock, and it sees the 3 clock ticks happen in 3.46 seconds, which is longer than expected. The moving clock appears to be ticking slowly. Now you might think that since time dilation is just the result of measuring the time component of a spacetime vector in different reference frames, that length contraction is just the result of measuring the space component of a spacetime vector in different reference frames. But this is actually not correct. Instead, length contraction is the result of measuring two different spacetime vectors in two different reference frames. Here we can see that the stationary rod is 3 units long, but the moving rod is 2.6 units long, which shows us that moving rods appear short. So this video is going to be longer than most videos you'll see on time dilation and length contraction. And this is because I want you to have a deeper understanding of how Lorentz geometry affects time and space. Before we do any calculations, I'm going to spend a bunch of time drawing pictures on spacetime diagrams with Lorentz transformations to make sure we understand spacetime geometry properly. After you have a deeper understanding of the geometry, I'll do some example calculations of time dilation and length contraction. So I've said this several times throughout this video series, but I'm going to say it again. Basis vectors and vector components are two sides of the same coin. Anytime we're dealing with vectors, we need to think about both the basis vectors and the vector components. It doesn't make sense to talk about one without also talking about the other. In Relativity 102, I introduced the idea that the same vector can have different components if we measure it using a different vector basis. It's important to remember that in special relativity, each reference frame has basis vectors and vector components. The reason that this is important to remember is because coordinate transformations, including the Lorentz transformation, will change both the basis vectors and the vector components, and they change in opposite ways. In Relativity 102, I showed that if we took basis vectors Ex and Ey and measured this pencil to have components 1, 1, if the basis vectors became twice as big, then the vector components would become twice as small, 1/2, 1/2. This is because basis vectors are covariant and vector components are contravariant, which means that they change in the opposite way that basis vectors do. We can see covariance and contravariance show up when we take the vector s and write it in array notation, with a row of basis vectors multiplied by a column of vector components. If we insert an identity matrix between the basis and components, we can break it up into a transformation matrix for the basis vectors and an inverse transformation matrix for the components. Here we can see that the opposite transformations balance out, and we can write the same vector s using a different basis with different components. In Relativity 103, we saw this was also true for the Galilean transformation, which is written in matrix form like this. Remember that to invert a Galilean matrix, we just change the sign of the velocity. So the Galilean matrices with plus v and minus v will multiply together to give the identity matrix. Just like before, we can change the components of a spacetime vector S to a new reference frame by changing the basis vectors with one Galilean matrix and changing the components with the inverse Galilean matrix. The opposite changes will balance out, and we can write the vector S in terms of a new basis with new components. And this same idea also applies to the Lorentz transformation. Remember, the beta coefficient in Lorentz transformations is just a fraction of the speed of light, v over c, so beta is a bit like a velocity. To invert a Lorentz matrix, we just need to change the sign of the beta coefficients. Gamma doesn't change sign because negative beta squared is the same thing as positive beta squared. If we ignore the gamma coefficients and just multiply the matrices, we find that we get a matrix with 1 minus beta squared on the diagonal. And if we include the gamma coefficients, multiplying the Lorentz matrices gives us a gamma squared out in front. If we plug this in for gamma squared, we get 1 over 1 minus beta squared. This cancels out with the 1 minus beta squared in the matrix, and we end up with the identity matrix. So we have shown that we can invert a Lorentz matrix just by changing the sign of beta. And once again, when we have a spacetime vector S written in array notation, we can change the basis vectors with one Lorentz matrix and change the vector components with the inverse Lorentz matrix. The opposite changes will balance out, and we can write the same spacetime vector S in terms of a new basis with new components. So hopefully you can see that with the Lorentz transformation, when the basis vectors do one thing with the Lorentz matrix, the vector components will do the opposite thing with the inverse Lorentz matrix. Let's see how this plays out geometrically using an example where Einstein is standing still and a car is traveling off to the right at 4/5 the speed of light. We know that the beta coefficient is just the fraction of the speed of light, v over c, so the beta coefficient is just 4/5. We also need to figure out the scaling factor gamma for the Lorentz transformation. If we plug in beta equals 4/5, we get gamma equals 1 divided by the square root of 1 minus 4 over 5 squared. 4 over 5 squared is just 16 over 25, and 1 minus 16 over 25 is just 9 over 25. The square root of 9 is 3, and the square root of 25 is 5, so the square root of 9 over 25 is just 3 over 5. And finally, 1 over 3 over 5 is just the reciprocal 5 over 3, so gamma equals 5 over 3 in this case. Now that we have beta and gamma for the Lorentz transformation between Einstein and the car, let's try changing from Einstein's spacetime basis, ET and EX, to the car's spacetime basis, ET tilde and EX tilde. Remember that the Lorentz transformation for vector components normally uses negative beta, and since the basis vectors change in the opposite way that components do, we change the sign of beta to be positive instead. Let's plug in beta equals 4 over 5 and gamma equals 5 over 3 into the Lorentz transformation equations. Now let's distribute the gamma value of 5 over 3 into the brackets. When we do 5 over 3 times 4 over 5, the 5 on top and the 5 on the bottom cancel out, and we get 4 over 3. Now that we have equations to change the basis according to the Lorentz transformation, let's try drawing out a picture to understand it better. The ET tilde basis vector equals 5 over 3 ET plus 4 over 3 EX. So we need 5 over 3, or 1 2/3 of the ET vector, and also 4 over 3, or 1 1/3 of the EX basis vector. And that gives us et tilde, as you can see here. Next, for ex tilde, we need 5 over 3 ex plus 4 over 3 et. So as expected, the Lorentz transform causes the time and position axes to bend toward each other like a pair of scissors, and the axes are also scaled by the gamma factor. Now let's try going in the reverse direction, going from the Carr's spacetime basis to Einstein's spacetime basis. Now remember, to reverse the Lorentz transformation equations, all we need to do is exchange the basis vectors and change the sign of the beta coefficients. So here we're changing the sign of beta from positive to negative. So all we're going to do to reverse the transformation equations is to put negative signs on these 4 over 3 coefficients after swapping the basis vectors. So to get et, we need 5 over 3, or 1 2/3 of et tilde, and then subtract 4 over 3, or 1 1/3 of ex tilde. Remember that when we subtract a vector, we reverse its direction. So instead of using plus ex tilde, which points to the upper right, we use negative ex tilde, which points to the lower left. And this gives us Einstein's et basis vector that we started with before. And also to get ex, we need 5 over 3 of ex tilde, and then subtract 4 over 3 of et tilde. And that also gives us the same ex vector we had before. So now, because we've reversed the Lorentz transformation, the spacetime basis vectors are bending away from each other, and also rescaled because of the gamma factor. So we can see that the Lorentz transformation can bring us from Einstein's spacetime basis to the Carr's spacetime basis, and back again. All we need to do is exchange the basis vectors and change the sign of the beta coefficient if we want to change the direction of the transformation. Now, one thing that might be surprising is that the gamma factor is positive 5 over 3 in both cases. You might think that it's impossible to scale by 5 over 3 to go from Einstein to the Carr, and then scale by 5 over 3 again to go back from the Carr to Einstein. But as we can see in these pictures, scaling by positive 5 over 3 in both the forward and reverse directions works out just fine. The key difference is that the beta coefficients are positive in one set of equations, which pushes the new basis vectors towards the upper right. But in the other set of equations, the beta coefficients are negative, and this helps pull the basis vectors back down to where they started. And of course, we can write out the basis change Lorentz equations in matrix form like this. Remember that basis vectors are covariant, and so we write them as rows and put them on the left side of the transformation matrix. This contrasts with vector components, which are contravariant, and so we write them as columns and put them on the right side of the transformation matrix. So at this point, our geometrical understanding of the Lorentz transformation is good enough, and we can start doing calculations with time dilation and length contraction. Again, we're going to see that geometrically, time dilation is really just about measuring the time component of a spacetime vector S in different bases. So if we have this spacetime vector S connecting a sneeze event and a clap event, time dilation is just measuring this vector with different basis vectors, and we'll get a different time component in each basis. So now let's say that Einstein is once again standing still, and from Einstein's point of view, the car is traveling to the right at half the speed of light. So the car's beta coefficient is 1/2. And you can check for yourself that with a beta value of 1/2, the corresponding gamma value is 2 over the square root of 3. So let's say that Einstein and the car start at the same time and place, which is the event where Einstein sneezes. Then, as they start traveling, Einstein claps his hands 3 time units later according to a clock in his own reference frame. Then the separation vector S between the sneeze and the clap is 3et plus 0ex in Einstein's frame. This means that the clap happens 3 time units after and 0 space units away from the sneeze. Now, if we want to find the time and position components for S in the car's reference frame, we need to use the Lorentz transformations to change the vector components. Since we use positive beta to change from Einstein's basis to the car's basis, we need to use negative beta to change from Einstein's vector components to the car's vector components. Again, this is because basis vectors are covariant and vector components are contravariant, and they transform in the opposite way that basis vectors do. First, we'll calculate the component ct tilde, the time of the clap according to the car. We'll start by plugging in beta equals 1/2 and gamma equals 2 over root 3. Then we'll plug in ct equals 3 and x equals 0. So the second term goes to 0, and we're left with 2 over root 3 times 3. The number 3 is just equal to root 3 times root 3. So we can do some canceling, and then we get that ct tilde equals 2 times root 3. Next, we'll calculate x tilde, the position of the clap according to the car. Again, we'll plug in beta and gamma, and then we'll plug in ct equals 3 and x equals 0. And again, the second term is 0, and so for the first term, the 2 on top cancels with the 2 on the bottom, and again, we cancel a factor of root 3, so we end up with x tilde equals negative the square root of 3. So in the car's reference frame, the components of the S vector are 2 times the root of 3 for time and negative root 3 for position. This means that for the car, the clap happens 2 times root 3 time units after and root 3 space units to the left of the sneeze. In decimals, this is 3.46 time units after and 1.73 space units to the left of the sneeze. Remember that since the position component x tilde is negative, this means that the sneeze happens to the left. This makes sense because the car is traveling to the right, and so it looks like the clap is happening behind it, off to the left. And we can see that this all matches up with our spacetime diagram. Einstein requires exactly 3 time vectors and 0 position vectors to get the spacetime separation vector S, which matches the components 3, 0. Meanwhile, the car needs about 3.5 time vectors and slightly less than 2 reversed position vectors to get S. This matches up with the components 3.46 and negative 1.37. So even though the man and the car are measuring the same vector S, they are clearly measuring different times between the sneeze and the clap. Einstein thinks they are 3 time units apart, and the car thinks that they are 3.46 time units apart. And the reason that Einstein measures 3 and the car measures 3.46 is because of the gamma factor. If we multiply Einstein's time measurement by the gamma factor, we get the car's time measurement, 2 times the square root of 3. So we have confirmed that the time measurements are in fact different for different reference frames. Now, another interesting question to ask is, instead of looking at the time between Einstein sneezing and clapping, let's take a look at the time between the sneeze and the driver of the car snapping their fingers. We'll denote the separation between the sneeze and the snap using the separation vector t. T is equal to exactly 3 time units in the car's reference frame, 3 et tilde plus 0 ex tilde. Now we can convert these to Einstein's components using the Lorentz transformation, but with positive beta coefficients this time because we're going in the reverse direction. And if we work it all out, we get that t for Einstein equals 2 times the square root of 3 time vectors plus root 3 position vectors. Once again, this works out geometrically. The car sees that the vector t is equal to exactly 3 time vectors, which matches the components 3, 0. Meanwhile, Einstein needs about 3.5 time vectors and slightly less than 2 position vectors to construct t. which matches the components of 3.46 and 1.73. And once again, the gamma factor is what converts the time in the car's frame, 3, to the time in Einstein's frame, 2 times the square root of 3. So we found that gamma, which is equal to or greater than 1, dilates Einstein's time ct into the car's time ct tilde. But we also found that gamma dilates ct tilde into ct. If we're not careful with our thinking, this seems like a contradiction. But it actually makes sense. When converting components from Einstein to the car, the S vector has a zero position component for Einstein, meaning that the first Lorentz transform equation becomes ct tilde equals gamma times ct. But when converting the components from the car to Einstein, it's the t vector that has a zero position component for the car, meaning that the first Lorentz equation in the reverse direction becomes ct equals gamma times ct tilde. There's no contradiction here because these two time dilation equations describe different vectors, s and t. In our space-time diagram, we can clearly see the s vector is made up of fewer time vectors in Einstein's frame, and so Einstein's time component ct is smaller than the car's time component ct tilde. But the t vector is made up of fewer time vectors in the car's frame, so here ct tilde is smaller than ct. Time between two events is always shortest when viewed from a reference frame where the two events happen at the same position. The time between the sneeze and the clap is shortest for Einstein because for him they happen at the same place, and the time between the sneeze and the snap is shortest for the car because for the driver they happen at the same place. This is why people say moving clocks run slow. A clock in its own frame will tick once per second, but a moving frame will see the clock tick once every gamma seconds. Time between clock ticks is always shortest in the frame of the clock. So hopefully you understand that time dilation is just the result of measuring spacetime vectors in different bases and getting different time components. Now, an easy mistake to make is to think that length contraction is just the result of measuring a spacetime vector in different bases and getting different position components. But this is actually very, very wrong. Here's why. In the ET-EX basis, lines of simultaneity are horizontal, so it makes sense to measure the length of this train using a horizontal vector r, because we are measuring the front and the back of the train at the same time. But in the ET-EX basis, lines of simultaneity are diagonal, so if we measure the train using this r vector, we're measuring the front, middle, and end of the train all at different times. This doesn't make sense. Instead, we should measure the train's length using a different vector m, which is parallel to the lines of simultaneity in the car's reference frame. So length contraction is actually about measuring the distance component of vectors along different lines of simultaneity in different bases. This means that for length contraction, each basis measures a different vector to get the length of an object. Let's do an example of measuring the length of a train that's stationary in Einstein's frame, with the car moving to the right. I've marked the world lines of the train's back and front on our space-time diagram. The length of the train in Einstein's frame is given by this capital R vector, a vector that connects the two ends of the train along Einstein's position axis. And let's say that Einstein measures the train to be lowercase r units long in this frame. The length of the train according to the moving car is given by this capital M vector, which connects the two ends of the train along the car's position axis. We'll say that the car measures the train to be lowercase m units long in the car's frame. The difference between capital R and capital M is this vector capital D, which is parallel to Einstein's time axis. So we'll write it as lowercase d times et. Hopefully it's clear that big M equals big D plus big R. We can rewrite each of these vectors using basis vectors as I've done above. Using the Lorentz transformation for basis vectors, we can rewrite ex tilde in terms of et and ex, and then distribute small m times gamma to each term inside. So on either side of the equal sign, we have a vector written in terms of et and ex. This means that the ex components must be equal to each other. So we get that small m times gamma equals small r, or equivalently, small m equals 1 over gamma times small r. Since gamma is always greater than or equal to 1, this means that 1 over gamma is always less than or equal to 1. This means that the length of the train in the car's moving frame, small m, is shorter than the length of the train in Einstein's rest frame, small r. So this means that moving objects are measured to be shorter in the direction of their motion. With a gamma factor of 2 over the square root of 3, a train that is 3 units long in the rest frame is measured to be 2.6 units long in the moving frame. The train's length is contracted to be shorter for the moving observer. We can also repeat this calculation for another train that's at rest with respect to the car, using a similar approach, but using the reverse Lorentz transformation this time. Once again, we get the result that the length is shorter in the moving frame when compared to the rest frame of the train. For the train at rest with respect to Einstein, Einstein measures it to be 3 units long, but the moving car measures the train to be 2.6 units long. And for this other train at rest with respect to the car measures it to be 3 units long, but Einstein measures it to be 2.6 units long. So when Einstein's train appears shorter to the car, and the car's train appears shorter to Einstein, there is no contradiction between these two statements. An object is always longest when measured in its rest frame, and it appears shorter to reference frames that are moving with respect to it. Just like time dilation, it might seem like length contraction formulas are self-contradictory, but you need to remember they each refer to a different train that we are measuring using different vectors. So length contraction is about measuring the distance component of different vectors along lines of simultaneity in different frames. The last thing I'll do is apply time dilation and length contraction to a practical situation involving muons. In Relativity 101, I said that a stationary muon will decay in about 2 microseconds on average. But if the muon is traveling at 0.995 times the speed of light, it will live for 20 microseconds on average due to time dilation. Let's draw a space-time diagram to understand this better, using one basis for the Earth's frame and another basis for the muon's frame. A reference frame with a beta value of 0.995 has a gamma factor of about 10, and so the Lorentz transformation of the basis vectors looks like this. Unfortunately, if I were to draw the muon's basis, et tilde and ex tilde, on a space-time diagram at the right scale, they would be very difficult to see because the beta and gamma factors are so big. So I'm going to draw them slightly wrong in a space-time diagram so that they are easier to see. This means that the arrows in my space-time diagram won't add up correctly, but I'm hoping you'll still be able to see the ideas of length contraction and time dilation in the space-time diagram, even if the scaling is a little bit wrong. So here we can see the world line of a muon being created in the Earth's atmosphere and decaying at the Earth's surface. If we measure the muon's world line using the muon's basis, we find that the muon lives for 2 time vectors. Let's say that we're working with units where this is about 2 microseconds. But if we measure the world line using the Earth's basis, we find that the muon lives for 20 time vectors, which is about 20 microseconds. Because the muon is moving with respect to the Earth sees the muon's lifetime dilated to be 10 times longer compared to a muon that's at rest. Now let's measure the distance between the atmosphere and the Earth's surface. In the Earth's frame, this distance requires a lot of position vectors to cross. It is very large, about 6.5 kilometers. But in the frame of the muon, this distance is contracted, since the muon thinks that the Earth is moving. We only need a couple of the muon's position vectors to cross it, so this distance is only about 650 meters. So according to the Earth, the muon lives for 10 times longer than expected, and that's why it's able to reach the Earth's surface from the atmosphere. But in the muon's frame, it only lives for 2 microseconds. But it still reaches the Earth's surface because the Earth's atmosphere is length contracted to be 10 times shorter. So to sum up this video, remember that time dilation is just the result of measuring the time component of a spacetime vector in different coordinate systems. Also remember that the time between two events is shortest when they are measured in a reference frame that sees them happen at the same position. All other times measured will be dilated to be bigger. And length contraction is just the result of measuring an object's length along different lines of simultaneity. Also, an object is physically longest when it is at rest, measured according to its own reference frame. All other lengths measured in different reference frames will be contracted to be shorter. Remember, the fact that moving observers see each other's clocks run slow and see each other's rods contracted to be shorter makes mathematical and geometric sense. It also agrees with the postulates of special relativity that say that all inertial frames are equivalent, and that no inertial frame is special compared to another.